Hello, GM everybody. It's Friday and we're in for another special workshop. We have Siqi Wang today who's going to be covering utilizing the Expander compiler collection. He's having quite a difficult setup, so let me just quickly invite him on stage and make sure that he's set up properly as we kick today's session off.
Hello.
We can hear you.
Can you hear me? Okay.
Yes, we can. Siqi will be off camera due to the limitations of his setup, but he will be able to share screen and guide you through his presentation. Just a quick overview, as I said, everybody, if you're looking for any of the recordings of the previous sessions as well as the slides, please make sure to refer to the hacker pack as well as an overview of the bounties that you can build for. Sechi, I can see you're ready, so without further ado, take it away. Thank you, everybody. Yeah, feel free to start.
Okay. So today I will talk about how to utilize the Expander compiler collection. With today's course, you will understand ECC's architecture and compilation process, and you will be able to write circuits using ECC's Rust frontend. You can use common circuit components and APIs. And also, you will be able to debug and optimize your circuits. First, let's see this question. What is Expander? Expander is the fastest Siqi proof system to date, and is developed by Polyhedron Network. It has two key components. One is the Expander Prover, and one is the Expander compiler collection. The Expander Prover has many subcomponents, but we will not talk about it today. There will be another bootcamp, another presentation for this several days later next week. And today's presentation is about the ECC. In the Expander architecture, we have the user writes a circuit code and then use the ECC compiler to compile it into layered circuits like this. And the Expander Prover can use this layered circuit to generate proofs. ECC transforms high-level code into layered circuits. It has multiple front-end language support. We will talk about it in next page. It has an extensive optimization pipeline and built-in testing and debugging tools. Finally, it has some standard circuits, which is similar as GNARC. In the ECC, in this page, we can see that the user code is processed by ECC and it outputs the layered circuit. But here is a detailed architecture. First, we have a source code. It can be Go or Rust. We have a front end for these two languages. And the source code will be converted into an intermediate representation. This then the IR is used for optimization. Then we have some circuit generation by a circuit builder. Finally, it outputs the layered circuit. We have Go and Rust frontend, and here is some features of them. The Go frontend is based on GNARC's frontend. So existing GNARC circuits can be used directly in the ECC. The Rust frontend is we can think it as a Rust rewrite of the Gnak frontend, but with some more features. Today's session is focused on the Rust frontend. We continue to go through this architecture. In the IR processing, we have this is the stage 1, the IR generation. It converts the source to intermediate representation. There is a builder. It parses source code and generates an initial IR structure. Then this IR structure will be optimized. There are multiple optimizations, such as dead code elimination, multiplication chain optimization, expression merging, constraint simplification, and layout optimization. Actually, there are more optimizations, but it's hard to list all of them. And the third stage is circuit generation. This is also the final process. In this stage, the IR is transformed into a layered circuit. So we need to place gates and connections. In later time of today's session, I will talk about these stages again with code examples, so you will be able to understand them better. Currently, ECC supports 3 fields: BN, BN and M31 and GF2. They have different features. The BN is standard in Ethereum, and it's optimal for pairing-based schemes. M31 is a Mersenne prime and is efficient for our common computers. And GF2 is a binary field, so it's ideal for Boolean circuits. Now I will talk about the APIs, such as how to write the circuit and how to use them to how to run, how to debug. First is a basic circuit declaration. We need to list all the input variables. Use the declare circuit macro. We can declare circuit structures like this. Also, we support some additional features, like you can declare arrays or public inputs. After declaration, we need to write the circuit logic. Here we need to implement this trait, and the logic is inside the define function. In this function, we can use something like builder.add or builder.multiply to do the addition and multiplication. The detailed APIs will be introduced very soon. There are roughly 6 categories of APIs. Firstly, is a basic operations. Like we can add 2 variables, sub 2 variables, multiplication and division. The 2 lines below is an example showing how to add 2 variables together, or how to multiply a variable by a constant. We have some other operations, like check whether a variable is 0, and convert this constant function is it converts a constant value to a variable. This function doesn't exist in Gnark, but in Rust we have to use a variable type, so we need this function. In these 2 pages, I didn't write the function. I didn't write the type for the arguments because they can. It's too long, and it's a trait, 2 variable or value, and it can be any variable or field elements or you unsigned int values. In the circuit, we need to make some assertions. So this is how to build the constraints. Basically, we have 3 types of constraints to assert something to constrain some variable to be 0 or non-zero or boolean. But actually, the non-zero and boolean constraints are converted to 0 constraints. It's done by the compiler, and it will be optimized. Hint is something to compute. We can use hint to compute something that is different to compute in the circuit. Like for the division, it's hard to compute division in the circuit, but we can compute it outside circuit and then verify the result in the circuit. This can be done use hints. It's similar with it's similar to that in Gnark. By the expander provers, we can get a random value in the circuit. This random value is almost a 0 cost in expander. It's very good. We can use it to we can use it in many scenarios, like in the log up. It's a very good lookup table. Subcircuits is the key point of the expander. So if we have many so let's think your circuit as a collection of many components, and maybe you will use one of the components many times. In this case, you can memorize it, and it will be a reference to your component, and the proving time, verification time will be very will be quickly than the normal case. And finally, we have some debugging tools. Like this display function, we can use builder display to show the value of a variable in debugging mode. Now I have go through the APIs, and now let's check how to compile a circuit or run a circuit and how to debug it. Firstly, this is a compilation function. We need to provide a circuit and some compile options to it. The result contains a witness solver and layered circuit. The witness solver handles additional inputs like the division or hints just as we mentioned before. And the layered circuit is a finally prover-ready circuit. Next, we need to generate the witness using witness solver. It's very simple. We firstly prepare the assignment and then call the solve witness function. Also, there is a debug evil function. We need to provide our circuit assignment and a hint caller to call it. Now it's time to do the live demo now.
Everybody, a quick reminder for your questions. Please make sure to post them in the questions area, and Sechi will be able to follow up with them afterwards.
Okay, so firstly, we need to suppose we are writing a new circuit. We have two ways. Some people will prefer to write some small circuits directly in the ECC repo. For example, we have some binary circuits and some example tests and some example circuits in the test directory. But in today's example, I will make another project. So firstly, I created the project, and here is the key point. Currently, the ECC and Expander must use Rust lightly, so we need to make some Rust toolchain file like this. Now we add ECC to our dependencies. Now the preparation is done. We can start to write our circuits now. Maybe. So first, we will declare the circuit like this. Suppose we want to prove that the 30th Fibonacci number with initial values A and B is equal to the target, like this. So now we can implement this trait. Now this function is done, and we can see that here we use the M31 config because we want to use M31 as our field. If you can choose other fields, or you can try to write something like this to support multiple fields. Next, we will compile the circuit. This is the function, and I will show you how to call it. The first argument is an instance of our circuit structure. And you see that our circuit structure has a template type. And for the compilation, it's actually variable that we can we don't need to write it explicitly. Next, we will prepare the assignment and witness. Here I will copy paste some code from my previous code. So in your real applications, maybe you will compute the input in another way, but here we just randomly select two numbers and really compute the same Fibonacci process, and finally set the target to the set our expected target to the real target. In the assignment, we also make a Fibonacci circuit instance, but this time the template argument is M31. It's our circuit field. Next, we will solve the witness. Yes, like this. With the witness, we can run the circuit and see whether the witness is correct or not. But please note, this layered circuit run is not proving. It's just to evaluate the circuit and check the results. Now let's run it. Here I use the release command to make it run So with this, it might the compilation time the Rust compilation time will increase a little bit, but the running time will be faster. But for this type of very small circuits, it's not significant. The running time is always very small. Okay, it's compiling, and since it's a first compilation, Rust will require some time to compile. Here I missed something. So, because we with this type of writing, the circuit now supports supports various fields. So we must specify the field here. But if you write some, but if you use a fixed field here, like M31 config, you don't need to do that. Okay, let's run it again. Okay, so now it's successfully executed. We can go through the code again. Now we continue to write some code. Firstly, I will show you how to debug and check the compilation results. For the debugging, let's try something like this. Here we use the display function to display the current number in each iteration. You can see nothing happened. That's because we are running in the compiling mode. If we want to see the values, we need to use the debug mode. That can be done with this. We have a default circuit and the assignment and the empty hint color. If you really need to use hints, there are real hint colors. Let's try it. Oh, so in order to use this debug evil, maybe we can use everything from extra. It's actually Expander Frontend extra. Okay, so this one also needs to specify the circuit, the type. That's also because we use this. I will show you what will happen if we use another one. Okay, so you can see that in the debug evil, every iteration is printed out. We can make some modifications. For example, make this to 100, and this also. Here you can see that these values become these values are modded by the Merson 31. But what if we change it to BN? Let's see. Okay, so these values are still printed out, but the form are the default display of BN is hex. So this is hex. Okay, so let's go back to M31, and I will show you what will happen if we use the fix the config in this define trait. Now this will be not necessary. And so with now let's see another thing. We can directly print out our compiled circuit. Let's see. The circuit is printed here. You can see that although we write something like add 100 times, but they are converted into into only 2 additions. So what does this mean? Here, firstly, we compute this phi. That's the input 0 and input 1 combined by some coefficients. This is the first layer. And in the second layer, we combine the previous outputs together. So this is -1. So we have the output of the second layer is actually this, subtract this. In the third layer, this value is multiplied by a random value. But why? Actually, we can do a small test. Let's change to 30 again. We can try to do some more assertions, like Obviously, this will not satisfy, but we can see what will happen in the circuit. Oh, you can see, now you can see in this debug eval, the assertion is failed, and we can use Rust backtrace to see where it happens. Now it only says in the debug eval something happened. So we remove the release, and let's run it in debug mode and see again. Okay, so here is where it happens. Line 26. Here. That's it. If we comment this line, we can check the circuit now. So you can see the first line is have some simple changes. In the first layer, besides computing A, besides computing B, it also computes A like this. And in the second layer, it combines these values together. And in the third layer, every value is multiplied by a random. But why random? Actually, that's how asserted equal works. Everything that we can, everything that is constrained to be equal, will convert it to something like this. Like this will equal to 0, and then these constraints will be combined together, like by using times random. And let's try to print some other things like the witness solver. Oh, maybe we can just print it using a debug trait. So you can see that there's nothing in the witness solver. That's because our circuit doesn't have doesn't have hints or divisions. And let's try to add some. So now the witness solver have many instructions. But mainly, the most important is this one. It computes the division of two variables and then output to the actual input of the circuit that will be provided to the prover. And so let's comment this. And next, we will try to generate a proof. Firstly, we run it. Okay, so now the circuit is satisfied, and we can dump it to files like this. So we now have the circuit.txt and witness.txt. Let's check the let's clone let's clone Expander repo and check out div. Then we can use in Expander's README. It provides how to run it. Here in the CLI section. Oh, here is another point. So in the expander, we expect the input to be SIMD, or to say, let's check it. Maybe like this. So it means we need to prove 16 instances in one time, but not one. Now let's generate it again. Oh, and here we need to solve witnesses. We can see that the wrong result become many true. Now switch back to Expander. Let's try to prove it. Okay, it's generated a proof. Proof.txt. Now let's continue to verify it. Oh, sorry, I mistyped. Okay, it says success, and that's it. We successfully go through the whole process, like writing circuits, debugging, running, and the proving, verifying process. Let's go back to the slides, and we have some standard library circuits. Currently, we have lookup, which is lookup tables. Poseidon M31 is hash function, and SHA-2. These components are available in the ECC repo, mainly in these two directories, circuit std-go and circuit std-rs. Finally, it's a best practices. For the circuit design, it's better to maintain a modular structure and reusable components. In circuit writing, you should define clear constraints. For optimization, you can use the memorization or to say subcircuits for repeated structures. Also, you will able to leverage built-in optimizations. For testing, you are encouraged to write test cases to make sure the coverage or edge cases. For resources, firstly, you can go to our documentation page. The URL is listed here. And in the repo of our two, in the repo of Expander and ECC, there are also some valuable things like the examples. We have Go and Rust examples for in these directories. Before the QA session, I have one final thing. So as I mentioned before, I will go through these stages again, and so let's do it. Maybe we can take Rust. So let's see what happens in this compile function. Actually, it contains two parts, the build generic and compile with options. The build generic is this type is mainly this part. It converts the Rust frontend to IR. And the compile with options is the main work of the compiler. It does all these other things. So we have a source IR. It goes through many steps and optimizations. Finally, we have the two output IRs, like the layer circuit. Okay, I think that's it. Now, if you have any questions, please ask me.
Hey, Sechi. So we've actually had just a single question in the questions tab, but Jennifer has been extremely active in the chat section and has been providing a lot of responses and answers. I don't know if you want to give a specific response for the one question we have at the moment.
Okay, so for that question, I think Jennifer's answer is Jennifer's answer is very good. So actually, I don't have very much experience in other in other circuit frontends. So Jennifer's answer is very good.
All right. Last questions, everybody. We are almost out of time for the workshop. So if you have any outstanding questions, now is the time to share them. As a reminder, I can see people asking in chat. The recording will be shared in the Hacker Pack, as we've always done. We'll make sure to post it also on Discord. We'll make sure to add it to our webpage. And so, yeah, please make sure to follow the link. It's been sent to you at the very beginning of the program, and we keep on sharing it in all of our sessions. Diego is asking a question in the chat section. Do you want me to read it out, or do you see it?
Yes, I see it. And for the day-to-day applications, I think maybe that's not the point of this. I mean,
just for everyone watching the recording, the question from Diego was, would be great to get examples on simple example for circuit generation. For example, verify that a business has been verified through a previous KYB process. And since there's a lot of literature on how to build more mathematical circuits, but missing more day-to-day applications.
Actually, I'm not familiar. I'm not familiar with how to convert the day-to-day applications to mathematical circuits. And I also think that as that type of skill is not related to how to use a compiler frontend. So I mean, it requires another dimension of ability. So maybe we will not include such examples.
All right, there's a new question that came in from Noor in the questions area. The question is, what inspired you to have another framework? Isn't the space too crowded already? And how do you plan to ensure adoption compared to others?
Okay. So for this question, I will ask it with some code. So actually, in our initial version of ECC, there is only a Go compiler. Let's see it. This Go compiler is very similar to the GNARC, and the circuit can be used in GNARC directly. Let's see the examples. So you can see even we need to import some Gnark libraries, and the function body is exactly the same. The only difference is how to compile and how to use it in the main function. And but why we have the Rust frontend? That's because we encounter some efficiency issues in Go, and all other parts are implemented in Rust. Like the expander is implemented in Rust, so we re-implemented an Gnark-like front end in Rust. That's it. And for your question, how do you plan to ensure adoption compared to others? I think for the front end, it's not very important to ensure adoption compared to others. So I think the front end is good enough. That's okay, and that's enough. What we need to do is just to ensure that Expander is the fastest Zk-proof system to date. So this will be the key point to Expander and ECC. Okay, any more questions?
Yeah, 0x Nagu followed up with not so sure what do you mean by day-to-day applications. If you have a statement that you want to prove without revealing some aspects of it, then you can apply the computational model. For example, if you want to prove you own a particular NFT or token, you own at least X balance of that token amount, you can apply this computation model to create a proof and verify that proof as it's needed.
Yes. This is the answer to the.
Yeah. I confused it for a question, but yeah.
Yes.
All right. Last questions, everybody. And thanks for the answer, 0x Nagu. Right. Let's end things here then. Thank you everybody for participating. As always, recording will be made available this time on Monday, as this one will not be so quick to process. But as a reminder, there is also several tracks that you can engage with and build something throughout this bootcamp and even compete for prizes. We have 5 different bounties that you can build for, each of which will can bring you up to $50,000 in grants. So please make sure to look through these in the hacker pack. You will find details on each, as well as a lot of reading materials that the Polyhedron team has provided to us. And if you are not sure who to build with, I advise that you go to our Discord. We have dedicated team formation channels, and also we've provided multiple links within the hacker pack where you can just fill in your profile. We have a dedicated builders dashboard where you can create a profile of yourself, say a few things about what your tech stack is, what are the things you can do, the things you cannot do, and what are you planning to build. You will be able to look through other profiles, and you will be able to team up. So if you do plan to work on the hacking bit of the bootcamp, please make sure to read through it, have a look at who the other hackers are, and hopefully team up. That is all for this week. Appreciate you all being so active, asking so many questions. It's been truly a pleasure to lead all these workshops, and looking forward to see you all next week for another full week of workshops, and we'll be sharing more details on a daily basis next week. Thank you all. Have a nice weekend. Enjoy thoroughly, and see you back next week.